In this video, we'll continue our discussion of graphing in 3-space by using a different technique. We actually see these quite a bit. They teach us in grade school what these kind of maps are, and then also a lot in like weather, we see this as well. So the shape we get when a plane intersects our surface at different levels along the x-axis, the dependent variable, that's what a level curve is. Take a picture of this. You guys have seen this probably in some kind of physical science class or something like that. But if I want to create like maybe a map that goes, I can show elevation, what we're going to use is a map like this down here. It projects your mountainside down onto a plane, right? A 3D space or whatever we're talking about, down onto a plane, and then they represent each height with numbers. So notice that if I were only looking at the shape and I'm walking up, okay, I'm going uphill to 1100, then 1200, 1300, 1400, and then this probably goes above in some way. But it shows the increase as we go from one to the other. Okay, so here's another example because this is going to be important. We're actually going to look at this with a lot of forces as well. We could look at this as a velocity map, as a contour map. It's very interesting. We'll get there. Okay, here is a couple other things I want to make sure you understand. Notice the map view. The steep slope is right here up this side, which is going to be around here, right? While the lighter slope would be here. This makes sense. You'd spend more time on each level creating a flatter incline, right? And then gentle slopes, you can see that these are gentle because there's more space in between. The heights also aren't as dramatic. But this is what a contour map, or in our case, we're going to call them level curves. So I gave some directions. A map of a level curve is a contour plot. That's what we're used to calling them. Define level curves. We just let the function equal k, a constant. So we can sometimes do this in general. Sometimes we'll do this in particular to figure out what's going on. All right, take a look at this graph here, or this example. Describe the graph. So we're just going to describe it of that. So we want to make a contour map. So I'm going to let the output be a constant. So I get k equals 49 minus x squared minus y squared. If I start working this out, okay, I got k squared equals 49 minus x squared minus y squared, right? X squared plus y squared, if I move those over, I get 49 minus k squared. Switching the sides. So let's start identifying what this is. All right. If I let k equal 1, I get x squared plus y squared equals 48. This is a circle with radius squared of 48. Okay, if I let k equal 2, I get x squared plus y squared equals 45. Right? That is a circle with radius squared of 45. If I let k equals 3, I get x squared plus y squared equals, okay, that's 49 minus 9, so 40. This is a circle with radius squared of 40. Okay, let's jump up there. Let's do k equals 6, right? That's x squared plus y squared equals, okay, 6 squared is 36. That's 413, so it's a square root of 13. Or it's going to be 13 on this side. And then the circle is going to have a radius of square root of 13. And then let's do one more. We'll do k equals 7. That's x squared plus y squared equals 0. This is just a single point. The only thing that gets me this is 0, 0. Okay, we have to try to make sense. Remember, these are z's, right? This whole column here are z's. So this is telling me a circle as we go higher and higher up on our plane. So let's go ahead. Let me throw a plane in here. Not to get too particular about it. All right. Let me flatten that because I know it'll bother somebody. I don't think that's flat. There we go. And I don't think this one's straight. There we go. Okay. And it moved on me. Leaving it alone. Okay, k equals, we should do maybe a k equals 0. Okay, k equals 0, that's at 0 height, we get x squared plus y squared equals 49. That's a circle with radius 7, right? So I'm going to start here. I'm going to go all the way out to 7. And we're going to create a circle. See if it'll fix it for me. With radius 7. I'll try to put this middle here. Cool. We'll move our 7 over. So that's our 7 now. Oops. That's our 7. We can extend these lines here. Okay. This is z equals 0. All right. We get that radius of 7. This is x. This is y. At z equals 0, maybe we should change this color. We get, it's too close. There we go. So that's z equals 0. And then if I go up, okay, we're going up to z equals 1. I get a radius of square root of 48. That is very close to the circle that is here. So I'm going to do a circle. And I know, I'll try to center it. This one's going to be real close to the one before. All right. There we go. Okay, this one is z equals 1. The next one, square root of 45. So this is going to be going a little... The gap is not the same, but it's bigger, right? So that was z equals 2. And then if I jump to z equals 3, it's a square root of 40. So now we're at between 6. The last one was between 6 and 7. So it's still not jumping up quite a bit. Still about the same, not too much further. But the distance does increase just a bit. Right? K equals 6. This radius is square root of 13. That's less than 4. So actually it jumps quite a bit. Put a circle right there in the middle. Oh, we didn't say that this was z equals 3. This one is going to be z equals 6. And then we got one more circle. Not even a circle, it's a point. This point here is z equals 7. So we had to use our mind here. That each inner circle is going further and further up in the z direction. So this is a cone, right? A cone turned over. But we use our z's to kind of give us some feel of 3 space. Okay, I got a few more examples for this one. I hope that one makes sense. You just got to pick k's and then show it on your contour map. Okay, so we're going to do, with some of these, we're going to do less of this, of like really getting into it, and more of like thinking about it. So let's take a look at this next example. Describe the graph of this function. So I have that function y squared minus x squared. I'm just going to let it equal k. Right, and then if I manipulate this, we can just flip it over really. Y squared minus x squared equals k. I know that didn't help a lot, but if I divide by k now, I got y squared over k minus x squared over k equals 1. Now, you may have to use your notes for this. This is a hyperbola. Hyperbolas along... And it actually changes based on k, if it's positive or negative. If k is negative, it'll flip the order. It'll be an x squared minus y squared. So along x or y, depending on the sign of k. Okay. So what that's going to look like, and I'm going to show you guys an actual GeoGebra graph. If I have this Cartesian plane, I'm going to have a bunch of parabolas going this way. And then I'm going to put this in a different color, but as soon as k changes signs, I'm going to have a bunch going this way. It's kind of hard to picture what that's going to even look like with what I've drawn. So let's check out GeoGebra. There we go. And I'm going to type that in. Z equals... y squared, was it y squared minus x squared? Okay, where's my square? Minus x squared. So we get this like, it's called a saddle. You can kind of see it here. See it goes down in one direction. So like if we look at it, you see that the red there is our hyperbolas in the green axis. I don't know which one's which in this case. They don't label them for us on here, unfortunately. But that is our parabola. But if I go to the other side and I go down, it is the other direction. So this is what happens with k being positive or negative. Remember, k represents our z value. So as z gets bigger in one direction, I get all these hyperbolas. But if z going negative in the other direction, I get that other side, creating this weird saddle-looking graph. All right, let's get back to our notes here. We're going to do another one just like that. So that's one thing I would be great with. This tells me what it looks like, hyperbolas along that. You could write saddle there. This would be a hard thing for me to assess you on, but it's going to be important to understand what this graph looks like, just like it was important to understand what normal functions looked like back in Calc 1 to help us with our understanding. All right, let's try another like this. And remember, we're just going to explain, and then we'll look at the 3D grapher to help us. All right, I have a logarithm of x minus y. So I let my z equal k, and I have ln of x minus y. Now, it may not be obvious here, but if we take e to each side, we know, okay, e to the k is just a constant, and then this gets rid of x minus y. Right? If I were to solve for y in this case, I get y equals x minus e to the k. Right? Hopefully you can figure out what that is. Okay, so what this is it's a line with slope of 1 and y-intercept of negative e to the k. So as k gets bigger and bigger and bigger, our y-intercept is going to go down. Right? It's going to be further and further and further down on the y-axis. With a slope of 1. So this is going to be lines with a slope of 1 with a y-intercept of negative e to the k. It's going to be kind of hard to draw, but I'm going to give it a shot. Okay, if k was 0, then it's minus 1. So if this is x and this is y, I don't know if I need that long axis. I accidentally drew it. 0, maybe we should do these. K equals 0 would be y equals x minus 1. So I get minus 1 and then a slope of 1. Right? That's k equals 1. K equals 0, sorry. Now we'll do k equals 1, which is going to be y equals x to the minus e to the 1. As this grows, minus e to the 2, minus e to the 3, as that's going up, that y-intercept is exponentially getting bigger. So what's happening is at first, yeah, we'll have a bunch of lines that look like this, right? In that same direction as that first line. But as we go further down, so we're going to have something there, and then the spacing will just start becoming a little bigger because the y-intercept is getting exponentially bigger with every time that we have a new one. So it's going to be going down like that with the space getting bigger, but as we get close to the inside here, we're going to get a bunch of little ones really close. Messing this up here. There we go. So if you try to use your imagination what that looks like, remember there are a bunch of straight lines, and then I get all z's, so they're going straight up and down. It looks like it's going to be like some kind of slope going down. So let's take a look at GeoGebra. And then let me throw this function in here. Okay, it was ln. Do I have that feature somewhere in here? Hold on. Math functions. ln. Cool. So, and then we'll just mess with this. It was x plus y. X plus y. All right, let me get rid of, there's a y out front. That definitely is going to make it different. There we go. Okay, so notice, let me go to looking down on the plane. So here's looking down on the plane. Let me make it look like our picture that we had. If it won't spin on me. Okay, notice that the lines get thicker as we're going up to the right, and then it's going under with k's going to negative. So it looks like our picture, we just did positive k's, but if I did negative k's, it's getting closer and closer. E to the k is never going to get to 0, but infinitely close. So that's why we get all these lines like dropping off like that, because as we let k equal negative, we're going to get a slope of 1, just like we had here, like that. But the e to the negative e to the k, as k gets bigger and bigger, and smaller and smaller and smaller, so we'd have like e to the negative 5,000. Remember that negative 5,000 in our exponent flips our fraction over. So it's actually going to make it where our y-intercept is never going to get to 0. It's going to get infinitely small, stay negative, but it's never going to get to 0. All right, let's jump back to our notes. All right, I have one more here. It says describe that graph, right? And we're going to we need k. So k equals, that's going to be our output, negative x plus 2y plus z minus 23. All right, I'm going to manipulate some things. I'm going to add 23 to the other side and then flip my equation over. So I got negative x, 2y plus z equals k plus 23. Now, if we look at this, our domain is 3D, so our graph is 4D. So graphing this is going to be pretty difficult, but what we can say is these, as k changes as we go up, we get planes, right? Hopefully you see that. If this was a number over here, I'd have a plane. We'd have planes with a normal, right? A normal vector of negative 1, 2, 1. The only thing that is changing is where that plane sits at. So as we change the k going up, the planes are just going to get higher and higher on the z, right? Or lower and lower in the z. So we can't really picture what this 4D graph's going to look like, but I can tell you that the contours, which is kind of weird, they're not in a plane, they're surfaces now. So I have just a crap ton of planes that are going to somehow make some kind of 4D graph. We can't sketch it. We could graph one of them and graph some maybe, but that's not going to help if you try to put a bunch of 3-dimensional planes on a 2-dimensional paper. It's going to be nonsense. So we're going to leave it like that we can talk about it. I can tell you that this 4D graph, the contours are a bunch of planes with that normal, but I can't tell you what that's going to look like in 4D because of our understanding of 4D.